What if I told you that nobody decided the speed of light? What if the speed of light isn't just a number some scientist measured in a lab, but rather the fundamental speed limit woven into the very fabric of reality itself, so essential that without it, you wouldn't have mass. Time wouldn't exist as you know it, and the universe would quite literally fall apart. And here's the real twist that's going to completely reshape how you see reality. Light doesn't actually travel at the speed of light. I know that sounds insane, but stick with me because by the end of this journey, you're going to understand why that statement is not only true, but reveals something so profound about the nature of existence that it will change how you perceive every moment of your life. The speed of light, that number you might remember from school, 299,792,458 meters per second, isn't just fast. It's not even primarily about light. It's the speed of causality itself, the maximum rate at which cause can lead to effect, the cosmic speed limit that separates past from future, and the reason you exist as a coherent being moving through time, rather than experiencing all moments simultaneously. And the wildest part? We didn't decide this speed. We discovered something far more strange, that this speed was decided when the universe itself was born, embedded in the structure of spacetime like source code in a program, determining everything from why you age, to why you have mass, to why the sun shines. Before we dive into this mind-bending journey through one of the universe's deepest mysteries, if you're ready to have your understanding of reality completely transformed, hit that like button right now. And subscribe, because this is going to be a wild ride through physics, philosophy, and the very nature of existence itself. Also, drop a comment telling me what country you're watching from, and what time it is where you are, because the speed of light is literally connecting us right now across space, and I want to see how far and wide our community spans across this planet. Let's start with what seems like a simple question. How fast does light travel? You might think that's easy. We have a number, right? But here's where things get weird immediately. The speed of light in a vacuum is exactly 299,792,458 meters per second. Notice I said exactly, not approximately, not rounded, exactly. And that word, exact, should make you suspicious, because in science, we rarely measure anything exactly. We measure things to increasing degrees of precision, always getting closer to the real value, but never quite hitting it perfectly. So why is the speed of light different? Here's the twist. The speed of light is exact because we defined it that way. In 1983, scientists essentially said, you know what? We're so confident we know the speed of light, and it's so fundamental to everything else, that we're going to define the meter based on the speed of light rather than the other way around. Think of it like this. Imagine you're trying to measure your room, but your measuring tape keeps changing length. Frustrating, right? So instead, you decide to nail down one thing as absolutely fixed. You say this particular stick is exactly 1 meter long by definition, and now we'll measure everything else against it. That's what we did with light. We said light travels exactly 299,792,458 meters per second by definition. And now we define what a meter is based on that. The distance light travels in 1/299,792,458th of a second. But here's what will blow your mind. We didn't choose that number arbitrarily. We chose it because that's what nature chose. We just measured what was already there. So who measured it first? This is where our story really begins, and it starts not with light, but with Jupiter. In 1676, a Danish astronomer named Ole Rachmer was doing something that seems completely unrelated to the speed of light. He was timing the eclipses of Io, one of Jupiter's moons. Io disappears behind Jupiter at regular intervals, like clockwork. But Rachmer noticed something strange. When Earth was moving toward Jupiter in its orbit, the eclipses happened earlier than predicted. when Earth was moving away from Jupiter. They happened later than predicted. Now, most astronomers at the time thought this was just observational error or something weird about orbits. But Rachmer had a radical idea. What if light takes time to travel? What if when Earth is closer to Jupiter, the light from Io's eclipse reaches us sooner, and when Earth is farther away, it takes longer? This was revolutionary because the prevailing wisdom, supported by none other than René Descartes, was that light traveled infinitely fast, that it arrived instantaneously. Even Galileo had tried to measure the speed of light with lanterns on distant hilltops and concluded it was too fast to measure. But Rachmer did the math. He calculated that light takes about 22 minutes to cross the diameter of Earth's orbit around the Sun. His calculation gave a speed of about 220,000 kilometers per second, which is actually pretty close to the real value, considering he was working in 1676 with telescopes that were basically fancy tubes with lenses. He was within about 26% of the true value, which is remarkable. But here's the really important part. Rachmer didn't decide the speed of light. He discovered that light has a speed, that it travels at a finite rate through space. Nature had already decided. Fast forward to 1849, and we get our first terrestrial measurement. French physicist Hippolyte Fizeau set up a clever experiment. He shined a light beam at a mirror 8 kilometers away, but between the light source and the mirror, he placed a rapidly rotating toothed wheel. The light would pass through a gap between the teeth, bounce off the distant mirror, and come back. If the wheel rotated at just the right speed, the returning light would be blocked by a tooth that had rotated into position while the light was traveling. By knowing the rotation speed and the distance, Fizeau calculated the speed of light at about 315,000 kilometers per second, getting even closer to the true value. Again, he didn't decide this speed. He measured what nature had already established. But here's where we need to pause and ask a deeper question, one that's going to set up everything that follows. Why does light have a speed at all? Why isn't it infinitely fast? And why that particular speed? When you flip a light switch, why does the light take time, even if it's an incredibly short time, to fill the room? What's limiting it? This question is going to take us deep into the structure of reality itself. But first, we need to understand what light actually is. And I promise you, the answer is stranger than you think. For most of human history, we didn't really understand what light was. We knew we could see with it. We knew the sun produced it. We knew it could be reflected and bent. But what was it actually? Was it a substance? A wave? A particle? The debate raged for centuries. Isaac Newton thought light was made of particles, what he called corpuscles. Others, like Christian Huygens, thought light was a wave. And here's what's absolutely wild. They were both right and both wrong in ways that reveal something deeply strange about reality. In the early 1800s, a British scientist named Thomas Young performed what's now called the double-slit experiment, and it's one of the most important experiments in the history of science. He shined light through 2 narrow slits onto a screen. If light were just particles, you'd expect 2 bright lines on the screen, one behind each slit. But that's not what happened. Instead, Young saw an interference pattern, alternating bright and dark bands. This is exactly what you get with waves. Think of it like dropping 2 pebbles in a pond. Where the ripples meet, they either add together, making bigger waves, or cancel out, making flat water. The bright bands were where light waves from both slits were adding together. The dark bands were where they were canceling out. Light, it seemed, was definitely a wave. But what was waving? Waves need a medium. Sound waves travel through air. Water waves travel through water. What was light traveling through? Scientists invented an answer: the luminiferous ether, an invisible substance that filled all of space and carried light waves. It sounds ridiculous now, but it was actually a reasonable hypothesis at the time. And this is where our story takes a crucial turn. because the search for the ether led to one of the most important negative results in scientific history. In 1887, two American scientists, Albert Michelson and Edward Morley, designed an experiment to detect the ether. Here was their reasoning. Earth is moving through space, right? It's orbiting the sun at about 30 kilometers per second. If space is filled with ether, then Earth is moving through this ether like a boat moving through water. And just like a boat experiences a current, Earth should experience an ether wind. This wind should affect the speed of light, depending on whether the light is traveling with the wind, against it, or perpendicular to it. Michelson and Morley built an incredibly sensitive device called an interferometer that could detect even tiny differences in the speed of light in different directions. They expected to measure the ether wind. Instead, they measured nothing. No matter which direction they pointed their interferometer, no matter what time of year it was, no matter how Earth was moving through space, the speed of light was always exactly the same. This result was so shocking, so unexpected, that Michelson himself considered the experiment a failure. But here's the mind-blowing part. This wasn't a failure. This was one of the most successful experiments in history because it revealed something absolutely fundamental about the universe. The speed of light is the same for all observers, regardless of how they're moving. Let me say that again because it's crucial. No matter how fast you're moving or in what direction, if you measure the speed of light, you always get the same answer. Always. This doesn't make intuitive sense at all. If you're on a train moving at 50 kilometers per hour, and you throw a ball forward at 20 kilometers per hour, someone standing still on the platform sees the ball moving at 70 kilometers per hour, right? You add the speeds. But light doesn't work that way. If you're on a spaceship moving at 90% the speed of light, and you shine a flashlight forward, someone at rest doesn't see the light moving at 1.9 times the speed of light. They see it moving at exactly the speed of light. You see it moving at exactly the speed of light. Everyone always sees light moving at the same speed. This seems impossible. It seems to violate basic logic. And yet, it's absolutely, experimentally, undeniably true. Every experiment ever done confirms it. But if the speed of light is always constant regardless of the observer's motion, something else has to give. And what gives is space and time themselves. This is where things get really wild, and this is what's going to hook you for the next section. If the speed of light is truly constant for all observers, then space and time cannot be constant. They must be flexible, stretchy, relative. And this realization came from a 26-year-old patent clerk working in Switzerland, thinking about trains and lightning bolts. In 1905, Albert Einstein published a paper titled On the Electrodynamics of Moving Bodies, and it's not an exaggeration to say this paper rewrote our understanding of reality. But here's what's fascinating. Einstein didn't start with complicated math or exotic experiments. He started with a thought experiment, a simple scenario he could visualize in his mind. And the setup is going to sound almost childish in its simplicity, but its implications are reality-shattering. Imagine you're standing on a train platform, and a train passes by at high speed. Right as the middle of the train passes you, two lightning bolts strike, one at the front of the train and one at the back, exactly simultaneously from your perspective. You see both flashes at the same time. But now consider someone sitting exactly in the middle of the train. From their perspective, they're not moving. The platform is moving past them. The train is their reference frame. When the lightning strikes, the light from both bolts starts traveling toward them at the speed of light. But here's the key. The train is moving forward, so the person on the train is actually moving toward the point where the front lightning struck and away from the point where the back lightning struck. Even though the light travels at the same speed in both directions, the person on the train will see the front lightning flash first and the back lightning flash second, because they moved toward one and away from the other. So from your perspective on the platform, the lightning bolts struck simultaneously. From the train passenger's perspective, the front bolt struck first. Who's right? This is the question that breaks our everyday intuition. The answer Einstein gave was both. Both observers are equally correct in their own reference frame. Simultaneity, the idea that two events happen at the same time, is not absolute. It's relative. It depends on your motion. Events that are simultaneous for one observer are not simultaneous for another observer moving relative to them. And this is only possible because the speed of light is constant for all observers. If light traveled at different speeds for different observers, you could do the math and figure out who was really moving and who was really at rest, who really saw simultaneous events. But because light always travels at the same speed, there's no absolute reference frame. Motion is relative, and simultaneity is relative. Now here's where your mind should start bending. If simultaneity is relative, then time itself must be relative. And Einstein showed that it is. Time literally passes at different rates for observers in relative motion. This is called time dilation. If you travel very fast relative to someone else, your clock runs slower from their perspective. Not because there's something wrong with your clock, but because time itself is passing more slowly for you. Think of it like this. Imagine time is a river, and the speed of light is the maximum current. When you're standing still, you're moving through time at the maximum rate. But when you start moving through space, you're redirecting some of that motion from the time direction into space directions. The faster you move through space, the slower you move through time. And the math works out such that no matter how you divide your motion between space and time, you always experience the speed of light as the same. Let me give you a concrete example that's been experimentally verified thousands of times. Particles called muons are created high in Earth's atmosphere when cosmic rays hit air molecules. These muons are unstable. They decay in about 2 microseconds. Given their speed and their lifetime, they shouldn't be able to reach Earth's surface. They should decay long before they get here. But we detect them at the surface all the time. Why? Because from our perspective, the muons are moving very fast, close to the speed of light, and so their internal clocks are running slow due to time dilation. What's 2 microseconds for them is much longer for us, giving them time to reach the surface. From the muon's perspective, if a muon could have a perspective, it still only lives 2 microseconds, but Earth's atmosphere is contracted, thinner, due to length contraction, so the muon doesn't have as far to travel. Both perspectives are correct. Both predict the muons reach the surface. And this brings us to the really big reveal. The speed of light isn't really about light. Light just happens to travel at this speed because light has a special property. It has no mass. The speed we call the speed of light is actually the speed of causality, the maximum speed at which information or influence can travel through the universe. It's the speed at which massless particles must travel. And anything with mass can never reach this speed. Why? Because of something Einstein revealed in the most famous equation in history. E equals mc squared. Energy equals mass times the speed of light squared. As you accelerate an object, you're adding energy to it. But because of this equation, adding energy doesn't just increase speed, it also increases mass. The faster you go, the more massive you become, and the harder it becomes to accelerate you further. To reach the speed of light, you would need infinite energy, because your mass would become infinite. The speed of light is an asymptote, a limit you can approach, but never reach if you have mass. So here's what's truly mind-blowing. The speed of light isn't a speed limit, because something is enforcing it, like a cosmic speed trap. It's a speed limit because of the structure of spacetime itself. The speed of light is woven into the very geometry of the universe. It's the exchange rate between space and time, the conversion factor that lets us measure them in compatible units. When we write the speed of light as c, we're not just talking about how fast light goes. We're talking about the fundamental structure of reality, and nobody decided this. It was decided by the universe itself, by the laws of physics, by whatever process brought spacetime into existence. But wait, there's more, and this is where things get even stranger. We need to talk about why this speed is what it is. Why not faster? Why not slower? And what happens at the moment of the Big Bang, when the universe itself was born? What if I told you that the speed of light being exactly what it is the reason you exist? What if changing it even slightly would make stars impossible, atoms unstable, and the universe a dead, empty void? The speed of light isn't just a number. It's part of a delicate balance of fundamental constants that make the universe life-permitting, and that should terrify and awe you in equal measure. Let's dig into why the speed of light is the speed it is. And here's the honest answer. We don't fully know. The speed of light falls out of Maxwell's equations, a set of 4 elegant mathematical equations written by James Clerk Maxwell in 1865 that describe electricity and magnetism. When Maxwell put his equations together, something remarkable happened. He found that oscillating electric and magnetic fields could propagate through space as waves, and when he calculated the speed of these waves, he got a number very close to the measured speed of light. Maxwell realized that light was an electromagnetic wave. But buried in his equations was something even more profound. The speed of these waves, the speed of light, was determined by 2 constants: the permittivity of free space and the permeability of free space. These constants describe how electric and magnetic fields interact with empty space. The speed of light equals 1 divided by the square root of permittivity times permeability. But this just pushes the question back a level. Why do the permittivity and permeability have the values they have? And this is where we hit something deep and mysterious. These constants seem to be fundamental features of the vacuum itself, of the underlying structure of spacetime. They're not derived from anything more fundamental that we know of. They just are what they are. It's like asking, why does the universe exist at all? Or why do the laws of physics take the form they do? We can measure these constants. We can describe how they relate to other phenomena. But we can't, at least not yet, explain why they have the specific values they do. Now here's where things get really interesting and a bit speculative, but based on solid physics. Imagine if the speed of light were different. What would happen? Let's say we doubled it, made it twice as fast. E equals mc squared becomes E equals m times 2c squared, which means E equals 4mc squared. Mass and energy are now related by a different factor. This changes everything. Nuclear reactions in stars depend on this relationship. Make the speed of light too high, and stars burn too fast, exhausting their fuel in thousands of years instead of billions. Make it too low, and stars might not be able to sustain fusion at all. The exact value of the speed of light is part of the Goldilocks zone of constants that make the universe habitable. But there's something even more mind-bending here. In our universe, the speed of light is constant everywhere, and at all times as far as we can measure. But was it always constant? Did it have the same value in the early universe, right after the Big Bang? Some physicists have proposed varying speed of light theories, suggesting that maybe in the first moments of the universe, the speed of light was different, and it evolved to its current value. These theories are controversial and not widely accepted, but they're trying to solve real problems, like why the universe looks so uniform in all directions, even though different parts of it seem to have been too far apart to influence each other if light always traveled at its current speed. The mainstream solution to this problem is inflation, a period of exponential expansion right after the Big Bang. But the varying speed of light theories offer an alternative. Maybe information could travel faster in the early universe, allowing different regions to come into equilibrium before the speed of light settled to its current value. Whether or not these theories are correct, they highlight something important. The speed of light is a feature of the universe, not something outside it. It's part of the package of physical laws that govern reality. And this raises a profound question. Could there be other universes with different speeds of light? In the multiverse theories that some physicists take seriously, our universe is just one bubble in a vast cosmic foam. And different bubbles might have different physical constants. In most of those universes, the speed of light might be too high or too low for complexity, for atoms, for life. We find ourselves in a universe with the speed of light we observe, because that's the only kind of universe where beings like us could exist to observe it. This is called the anthropic principle, and it's either a profound insight or a cop-out, depending on who you ask. But let's bring this back to something concrete and testable. The constancy of the speed of light is one of the most precisely tested facts in all of physics. We've measured it in laboratories, in Earth orbit, using distant astronomical objects, and it's always the same within our measurement precision. But here's a wild fact. We've even tested whether the speed of light has changed over billions of years. How? By looking at distant quasars and measuring the ratios of light at different wavelengths. These ratios depend on the fine structural constant, which in turn depends on the speed of light. By analyzing light that's been traveling through space for billions of years, we can ask, was the speed of light different in the distant past? And the answer, as far as we can tell, is no. The speed of light has been constant across cosmic time to within a few parts per million. Think about what that means. Light from distant galaxies, emitted when the universe was a fraction of its current age, traveled through expanding space for billions of years, and arrived here with properties that tell us the speed of light was the same back then as it is now. The universe has expanded. Galaxies have formed and evolved. Stars have been born and died. But this fundamental constant has remained constant. And this constancy is what allows us to look back in time at all. Every time you look at a distant object, you're seeing it as it was in the past because light takes time to travel. The farther away something is, the farther back in time you're seeing. The entire field of cosmology depends on the speed of light being constant. We can map the history of the universe because light is a cosmic messenger, and its speed is the conversion factor between distance and time. But here's the hook for the next section. I told you at the beginning that light doesn't actually travel at the speed of light. Are you ready for that reveal? Because it's going to change how you understand what light really is. Here's the truth. Light, in a vacuum, always travels at the speed of light. But the moment light enters any material, glass, water, air, even the thin gas between stars, it slows down. You've seen this effect. It's why a straw looks bent in a glass of water, why lenses work, why prisms split white light into rainbows. This slowing is called refraction. But here's the question nobody really asks. What's slowing the light down? Is it bumping into atoms like a ball bouncing through a pinball machine? No, the reality is much stranger and more beautiful. When light enters a material, it starts interacting with the electrons in the atoms of that material. The light's electromagnetic field causes the electrons to oscillate, to vibrate. These oscillating electrons then emit their own electromagnetic radiation. So the light you see coming out the other side isn't the original light. It's new light, emitted by electrons that were stimulated by the original light. And here's the key. There's a slight delay in this process. The electrons take time to respond and re-emit. This delay means the overall speed of the light wave through the material is slower than it would be in a vacuum. We describe this with something called the refractive index. A vacuum has a refractive index of 1. Water has a refractive index of about 1.33, meaning light travels about 1.33 times slower in water than in a vacuum. Diamond has a refractive index of 2.42. Light slows down dramatically in diamond, which is part of why diamonds sparkle so brilliantly. The slow speed and resulting refraction cause light to bounce around inside the diamond before emerging. But here's where things get wild. In some specially prepared materials, you can slow light down to walking speed. In 1999, physicist Lin Hao and her team at Harvard slowed light to 17 meters per second, about 38 miles per hour, by shining it through a cloud of ultra-cold sodium atoms cooled to within a few billionths of a degree above absolute zero. In this state, called a Bose-Einstein condensate, the atoms act collectively in strange quantum ways, and the light interacts with them so strongly that it slows to a crawl. Hao's team later managed to stop light completely, storing the information in the atomic medium and then releasing it later. Light came to a complete stop and then started again. Now you might think, okay, so light slows down in materials. Big deal. But think about what this means for your everyday experience. When you look at something, light bounces off it, travels through air, passes through the lenses of your eyes, which slow it down, and then is detected by your retina. The image you see is assembled in your brain from light that has been slowed, refracted, and processed. You're not seeing things as they are in real time. You're seeing them as they were a few nanoseconds ago, after light traveled from them to you. For distant objects, the delay is more noticeable. When you look at the sun, you're seeing it as it was 8 minutes ago, because that's how long light takes to travel from the sun to Earth. If the sun suddenly vanished, we wouldn't know for 8 minutes. We'd still see it in the sky, still feel its warmth from light that was already on its way, living on borrowed time. The nearest star beyond our sun, Proxima Centauri, is 4.2 light-years away. When you see Proxima Centauri, you're seeing it as it was 4.2 years ago. The Andromeda Galaxy, our nearest large galactic neighbor, is 2.5 million light-years away. The light you see from it left when our human ancestors were just emerging on Earth. You're literally looking back in time. And the most distant objects we've observed, ancient galaxies near the edge of the observable universe, show us what the universe looked like over 13 billion years ago, less than 1 billion years after the Big Bang. Their light has been traveling toward us for most of the age of the universe. But here's something even weirder. What does light experience during its journey? This is where physics gets truly strange. From our perspective, light takes time to travel. From light's perspective, if we could imagine having light's perspective, the journey is instantaneous. Why? Time dilation. Remember, as you approach the speed of light, time slows down. At the speed of light, time dilation is infinite. Time stops. From a photon's perspective, it is emitted and absorbed in the same instant. Zero time passes. The photon doesn't experience duration. It doesn't age. In a very real sense, from the photon's point of view, the entire universe along its direction of travel is contracted to zero length. The moment of emission and the moment of absorption are the same moment. The photon exists in a timeless eternal now. Think about that. Right now, photons from the Big Bang, from the cosmic microwave background radiation, are hitting your body. These photons have been traveling for 13.8 billion years from our perspective. From their perspective, no time has passed at all. They are simultaneously at the moment of the Big Bang and the moment of hitting you. Past, present, and future are one for light. This is what it means for the speed of light to be the cosmic speed limit. It's not just the fastest speed. It's the boundary between our time-bound existence and something timeless. And here's a question that should haunt you. Why are we limited to experiencing time sequentially, moment by moment, while light experiences everything simultaneously? The answer is mass. We have mass, light doesn't. Mass ties us to the flow of time. It slows us down through time by limiting our speed through space. The speed of light is the barrier that separates the massive from the massless, the temporal from the timeless. And nobody decided this. It's built into the structure of the universe. Now we need to talk about something that's going to make everything we've discussed so far seem almost simple by comparison. What happens to the speed of light in the quantum realm, where particles behave in ways that defy classical intuition? Because here's what will blow your mind. The speed of light is still the cosmic speed limit, but in the quantum world, particles can seem to appear to violate it through a phenomenon called quantum tunneling. And information can appear to jump between entangled particles instantaneously. And we still don't fully understand how these phenomena respect the cosmic speed limit. Or maybe they reveal that the speed limit is more subtle than we thought. Let's start with quantum tunneling. In quantum mechanics, particles aren't point-like objects with definite positions. They're described by wave functions, probability clouds that tell you where the particle is likely to be if you measure it. One consequence of this is that particles can sometimes pass through barriers that classically they shouldn't be able to cross. Imagine throwing a ball at a wall. Classically, if the ball doesn't have enough energy to break through or go over, it bounces back. But quantum mechanically, there's a small probability that the ball appears on the other side of the wall without ever having physically traveled through it. This is tunneling. And here's the weird part. During the tunneling process, the particle seems to cross the barrier faster than light would cross it. Some experiments have measured tunneling times that suggest the particle traversed the barrier instantaneously, or even in negative time, appearing on the other side before it entered. Does this violate the speed of light limit? Physicists argue no, and here's why. You can't use tunneling to send information faster than light. The tunneling is probabilistic and random. You can't control which particles tunnel and which don't in a way that would let you encode a message. So while individual particles might tunnel faster than light, no information or energy is transmitted faster than light on average. The cosmic speed limit remains intact, but the details are subtle and still debated. Now let's talk about quantum entanglement, because this is where things get really spooky. Einstein called it spooky action at a distance, and he meant it as a criticism, but the spookiness turned out to be real. Here's the setup. You can create two particles that are quantum mechanically entangled, linked in such a way that the state of one particle is correlated with the state of the other, regardless of the distance between them. If you measure one particle and find it has a particular property, like spinning up, you instantly know the other particle, even if it's on the other side of the galaxy, has the opposite property, spinning down. The measurement of one seems to instantaneously affect the other. Einstein hated this. He argued it couldn't be real, that there must be hidden variables, properties the particles had all along that we just weren't measuring, like two people wearing one of a pair of gloves. When you find a left glove, you know the other person has a right glove, but nothing spooky happened. The gloves were always left and right. But in 1964, physicist John Bell derived an inequality that could distinguish between Einstein's hidden variables and genuine quantum entanglement. And when experiments were done, most definitively by Alan Aspect in the early 1980s, Bell's inequality was violated. Quantum entanglement is real. The particles genuinely don't have definite states until measured, and the measurement of one particle does instantaneously affect the other. But here's the crucial point. This still doesn't let you send information faster than light. When you measure your particle, you get a random result, spin up or spin down, 50-50. The person with the other particle also gets a random result. It's only when you compare notes, which requires sending information at or below the speed of light, that you discover the correlations. You can't use entanglement to send a message faster than light. Again, the cosmic speed limit holds, but in a subtle way. Nature seems to conspire to prevent faster-than-light communication, even when instantaneous correlations exist. There's a deeper principle at work here called causality. The speed of light isn't just about how fast things move. It's about cause and effect. In relativity, the speed of light defines the structure of causality. Events can only influence each other if they're within each other's light cones, the region of spacetime that can be reached by traveling at or below the speed of light. If you could send information faster than light, you could, in principle, send it backward in time in some reference frames, creating paradoxes. You could receive a reply before you sent the message. The universe seems to avoid this. The cosmic speed limit protects causality. But here's something that should make you pause. We've discovered that empty space, the vacuum, isn't truly empty. It's filled with quantum fluctuations, virtual particles popping in and out of existence on timescales so short they don't violate the uncertainty principle. These fluctuations affect the properties of particles moving through the vacuum. They even affect the speed of light, very slightly. Over vast cosmic distances, high-energy light and low-energy light can travel at fractionally different speeds due to quantum effects. This has been measured for gamma rays from distant cosmic explosions. The differences are tiny, parts per million after traveling billions of light years, but they're real. Does this mean the speed of light isn't truly constant? Not quite. It means the vacuum isn't truly a vacuum. There's structure there, quantum foam some call it, and it affects light. But the underlying speed limit, the speed of light in an idealized, perfect vacuum, remains constant. It's the structure of spacetime itself. Now here's the hook for the next section. All of this, relativity, quantum mechanics, the constancy of the speed of light, it's all part of our current best understanding of physics. But there are cracks. There are places where our theories break down. And one of the biggest cracks is at the very beginning of the universe, the Big Bang, and at the hearts of black holes, where space-time itself becomes so warped that our equations give nonsense answers. What happens to the speed of light under those conditions? And what might a deeper theory, a theory of quantum gravity, reveal about the true nature of this cosmic speed limit? We've reached the frontier, the edge of what we know, and the beginning of what we're trying to figure out. And here's what's humbling. Despite everything we've learned about the speed of light, despite centuries of experiments and brilliant theories, there are fundamental questions we still cannot answer. What happens to the speed of light inside a black hole? What was its role in the first moments of the Big Bang? And could there be phenomena in the universe that travel faster than light without violating causality? These aren't just academic questions. The answers could reshape our understanding of reality itself. Let's start with black holes, because they represent one of the most extreme tests of our understanding of the speed of light. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape once it crosses a boundary called the event horizon. Think about what that means. The speed of light is supposed to be the cosmic speed limit, the fastest anything can go. But inside a black hole, even traveling at the speed of light isn't fast enough to escape. How is that possible? The answer reveals something profound. The speed of light is still the cosmic speed limit inside a black hole, but space-time itself is so warped, so curved, that all paths lead inward. Imagine you're on a river that's flowing toward a waterfall. If the current is stronger than your maximum swimming speed, you can't escape even if you swim as fast as possible. You can swim at your top speed, but relative to the riverbank, you're still moving toward the falls. That's what happens inside a black hole. Light travels at the speed of light relative to the local spacetime, but spacetime itself is falling inward faster than light can climb out. At the very center of a black hole lies the singularity, a point where density becomes infinite and spacetime curvature becomes infinite. Our equations break down there. General relativity, Einstein's theory of gravity, predicts the singularity but can't describe what happens at it. Quantum mechanics should become important at such small scales, but we don't have a complete theory of quantum gravity that can handle it. What happens to the speed of light at a singularity? We don't know. Does it still make sense to talk about speed when spacetime itself is shredded? These are open questions. In 1974, Stephen Hawking discovered something shocking. Black holes aren't entirely black. Due to quantum effects near the event horizon, black holes emit radiation, now called Hawking radiation. Virtual particle pairs form at the horizon. Normally, these pairs would annihilate each other almost immediately. But at the horizon, one particle can fall into the black hole while the other escapes. The escaping particle becomes real radiation. Over immense timescales, far longer than the current age of the universe for stellar mass black holes, this radiation causes the black hole to evaporate. Now here's what's mind-bending. This radiation appears to carry information out of the black hole, but in a scrambled form. How does information encoded in matter that fell into the black hole get transferred to radiation escaping from outside the horizon without anything traveling faster than light? This is the black hole information paradox, and it's one of the deepest unsolved problems in theoretical physics. Recent work suggests that the information might be encoded in subtle correlations in the Hawking radiation, correlations that respect the speed of light limit but are incredibly complex, requiring knowledge of the entire radiation history to decode. Some physicists propose that the event horizon isn't a sharp boundary, but a fuzzy quantum region called a firewall, wherein falling information is violently scrambled and re-emitted. Others suggest that black holes might be connected to other regions of spacetime through wormholes, and information might traverse these shortcuts, though even through a wormhole, local speeds never exceed the speed of light. We're still figuring this out. The speed of light remains the speed limit, but how information respects that limit in extreme conditions is at the cutting edge of research. Now let's rewind to the opposite extreme. The Big Bang, the moment the universe began. According to our best current model, the universe started in an incredibly hot, dense state about 13.8 billion years ago and has been expanding ever since. But what happened in the very first moments? In the first fraction of a second, the universe went through a period called inflation, where it expanded exponentially fast, faster than the speed of light. Wait, you might say, I thought nothing could go faster than light. And you're right, but there's a subtle distinction. Space-time itself can expand faster than light. Objects moving through space-time are limited to the speed of light. But space-time itself isn't a thing moving through something else. It's the fabric of reality, and it can expand, carrying objects along with it at any rate. During inflation, regions of space that started very close together were carried apart faster than light could travel between them. This doesn't violate relativity, because the objects aren't moving through space faster than light. Space itself is expanding between them. In fact, this is happening right now. The universe is expanding, and distant galaxies are being carried away from us by the expansion of space. Galaxies more than about 14 billion light-years away are receding from us faster than the speed of light due to expansion. We can never see them because their light can never reach us. It's being carried away by expanding space faster than it's traveling toward us. There's an edge to the observable universe, a cosmic horizon beyond which we can never see, not because the light hasn't had time to reach us yet, but because it never will. The expansion of space creates a permanent divide, and this horizon is expanding. As time goes on, more galaxies cross this horizon and disappear from view forever, their light redshifted to infinite wavelengths, fading to nothing. But here's something that should really bake your brain. In the far future, trillions of years from now, if the expansion of the universe continues to accelerate as current observations suggest, all galaxies beyond our local group will have crossed the horizon. Future civilizations, if any exist, will look out at the universe and see only their own galaxy surrounded by darkness. They'll have no evidence that other galaxies ever existed. They'll have no evidence of the Big Bang. The cosmic microwave background radiation will have been redshifted to undetectability. All the evidence we have today for the history and structure of the universe will be gone. They'll live in an island universe, alone in the dark, with no way to know there was ever anything more. The speed of light and the expansion of space will have erased the cosmic context. This is called the cosmic censorship of history. We're living in a special time, a cosmic window, where we can still see the deep past and the vast universe. The speed of light is both what allows us to see back in time and what will ultimately hide most of the universe from future observers. Now, could there be anything that travels faster than light? There are some speculative possibilities that don't violate the fundamental principles. One is the Alcubierre drive, a theoretical concept proposed by physicist Miguel Alcubierre in 1994. The idea is to create a bubble of spacetime that contracts space in front of a spacecraft and expands it behind. The spacecraft itself doesn't move through space faster than light. It rides a wave of spacetime. Inside the bubble, the spacecraft is at rest relative to local spacetime. But the bubble itself moves, potentially faster than light, carrying the spacecraft with it. This doesn't violate relativity, because again, spacetime can do what it wants. The spacecraft isn't locally exceeding the speed of light. The catch? Creating an Alcubierre drive would require exotic matter with negative mass or negative energy density, something we've never observed and which may not exist. It would also require enormous amounts of energy, possibly more than the entire mass energy of the observable universe converted to usable form. And there are causality concerns. Some calculations suggest an Alcubierre drive could be used to create closed time-like curves, paths through spacetime that loop back on themselves, time travel. If time travel creates paradoxes, nature might have a way of forbidding Alcubierre drives. We don't know. It's mathematically possible within general relativity, but practically and perhaps fundamentally impossible. The speed of light remains, as far as we can tell, an absolute barrier for anything carrying information or energy through normal spacetime. But here's the thing. Our current theories, general relativity and quantum mechanics, are incomplete. We know they're incomplete because they give different, incompatible answers in certain situations, like at the Big Bang singularity or inside black holes. We need a theory of quantum gravity, a theory that unifies quantum mechanics and general relativity into a single consistent framework, and we don't have one yet. String theory is a candidate. Loop quantum gravity is another. There are others, but none are confirmed. And any such theory might change our understanding of what the speed of light really is at the deepest level. Some versions of string theory suggest that spacetime itself is emergent, not fundamental. At the smallest scales, the Planck scale, about 10 to the negative 35 meters, spacetime might dissolve into something more abstract, a network of quantum information or vibrating strings in higher dimensions. If spacetime is emergent, then the speed of light, which is a property of spacetime, is also emergent. It arises from something deeper. But what? We don't know yet. This is the frontier. This is where the next generation of physicists will work. And the answer, when we find it, might reveal that the speed of light is even stranger and more fundamental than we currently imagine. Or it might show that it's a derived property, an approximation that holds in our low-energy, large-scale universe, but breaks down in the quantum foam. Here's the hook for the next section. We've been talking about the speed of light as something out there, a property of the universe. But it's also intimately connected to you, to your existence, to your perception of reality. And understanding that connection is going to change how you experience every moment of your life. Let's bring this back to you, sitting here right now, watching or listening to this video. The speed of light isn't just an abstract cosmic principle. It's woven into your every experience. Every thought you have, every sight you see, every moment you experience is shaped by the speed of light in ways you've never consciously realized. And once you understand these connections, you'll never perceive reality the same way again. Let's start with vision. Right now, you're seeing these words, or you're seeing the world around you. But what you're actually experiencing is light that bounced off objects, traveled through space, passed through your eye's lens, and struck your retina. Your retina contains cells called rods and cones that contain molecules called photopigments. When a photon hits a photopigment molecule, it causes a chemical change, isomerization, where the molecule changes shape. This shape change triggers a cascade of chemical reactions that ultimately produces an electrical signal that travels along your optic nerve to your brain. Your brain processes these signals and constructs the image you perceive. This entire process takes time. The absolute minimum time for visual processing, from photon hitting retina to conscious awareness, is about 50 to 100 milliseconds, a tenth of a second. But here's the thing. The photon itself took time to travel from the object to your eye. For nearby objects, it's nanoseconds, billionths of a second. But it's still time. What this means is that you're never seeing the present. You're always seeing the past. When you look at your hand in front of your face, you're seeing it because it was a few nanoseconds ago. When you look at someone across the room, you're seeing them as they were a few tens of nanoseconds ago. When you look at the moon, you're seeing it as it was 1.3 seconds ago. The person you're looking at, the world you're perceiving, it's all history. The present, the true present, is inaccessible to you. You live in a bubble of delayed information, a personal past light cone, forever chasing a present you can never quite reach. Now let's think about communication. When you talk to someone, your words travel as sound waves at about 343 meters per second through air. That's slow compared to light. If you're 10 meters away from someone, your words take about 30 milliseconds to reach them. Then their brain takes time to process the sounds and extract meaning. They formulate a response, which takes more time. Their words travel back to you. More processing time. There's a fundamental delay in all human communication, a lag imposed by the finite speed of information transfer. We're not directly connected. We're isolated islands exchanging signals across the gap, and those signals take time to cross. In the modern world, this becomes even more apparent. When you make a phone call across continents, your voice is converted to electrical or optical signals, transmitted through cables or satellites, and reconstructed at the other end. The speed of light in fiber optic cables is about 2/3 the speed of light in a vacuum. A signal traveling halfway around Earth, about 20,000 kilometers, takes about 100 milliseconds to make the journey. That's the one-way light time. Round trip is 200 milliseconds. You can actually notice this in intercontinental calls sometimes, that slight delay between speaking and hearing a response. It's not just processing time. It's the finite speed of light imposing itself on your conversation. For astronauts on the moon, the communication delay was much more obvious. The moon is about 384,000 kilometers away. Light takes 1.3 seconds to travel from Earth to Moon. So when Mission Control spoke to the Apollo astronauts, there was a 2.6-second round-trip delay. You can hear it in the recordings. Mission Control asks a question. Silence. The astronaut responds. More silence. Then Mission Control hears the response. It's a conversation fractured by the speed of light, a reminder that even in communication, we're bound by the cosmic speed limit. Now let's think bigger. Your entire existence, your sense of continuity, of being a person who persists through time, depends on the speed of light and the way it structures causality. Your brain is a network of about 86 billion neurons, each connected to thousands of others. Information flows through this network as electrical impulses, action potentials, traveling along axons at speeds ranging from about 1 meter per second for unmyelinated fibers to about 100 meters per second for myelinated fibers. That's much slower than light, but it's the speed at which your thoughts propagate. It takes time for information to travel from one part of your brain to another. Your brain isn't a single unified entity, experiencing everything simultaneously. It's a distributed network, and different parts process different information at different times. Your sense of unity, of having a single coherent experience, is an illusion constructed by your brain to make sense of these distributed, time-delayed processes. Experiments have shown this in startling ways. In the 1980s, neuroscientist Benjamin Libet performed experiments measuring the timing of conscious decisions. He asked people to spontaneously decide to move their finger and note the exact time they felt they made the decision. Meanwhile, he measured brain activity with EEG. He found something disturbing. The brain showed activity related to preparing the movement about 500 milliseconds before the person reported consciously deciding to move. Your brain was already acting before you were consciously aware of deciding. What does this mean for free will? That's a whole other rabbit hole. But the point here is that consciousness, decision-making, selfhood, all of it unfolds in time at speeds much slower than light, and the delays and timings matter. The speed of light sets the ultimate limit, but even our neural processing is slow enough that temporal structure matters. Here's another angle. Your existence depends on the speed of light being what it is, because it determines how atoms work. The stability of atoms, the energy levels of electrons, the way electrons orbit nuclei, all of this depends on electromagnetic interactions, which propagate at the speed of light. The fine structure constant, a dimensionless number that describes the strength of electromagnetic interactions, is approximately 1 divided by 137. This constant depends on the speed of light. Specifically, it's proportional to the square of the electron charge divided by the speed of light times Planck's constant. Change the speed of light, and you change the fine structure constant, and you change how atoms behave. Make it too different, and atoms might not be stable. Chemistry would be different or impossible. The molecules that make up your body wouldn't exist. Life wouldn't exist. You exist because the speed of light is what it is. On a more profound level, the speed of light determines the structure of spacetime, and spacetime is the arena in which causality plays out. Causality is the idea that causes precede effects, that there's an arrow of time, that the past influences the future, but not vice versa. This arrow, this structure, is built into the geometry of spacetime by the cosmic speed limit. Without it, time might not flow. Events might not have a clear order. The universe might be a static, timeless block where all moments exist simultaneously with no distinction between past and future. But the speed of light creates the distinction. It separates spacetime into regions that can influence each other and regions that can't, creating the structure of past, present, and future. You experience time flowing because you're embedded in this structure. You move through time, and the speed of light is the exchange rate between time and space, the factor that determines how your motion through space affects your motion through time. Think about it this way. Right now, in this moment, you're moving through time at 1 second per second from your own perspective. If you start moving through space, your rate of motion through time slows down from an external perspective due to time dilation. The faster you move through space, the slower you move through time. At the speed of light, you'd stop moving through time entirely. Your entire world line, your entire history from beginning to end, would be compressed into a single instant from your perspective. The speed of light is the boundary between temporal existence and timeless existence. And you're on this side of the boundary because you have mass. Mass is what traps you in time, what forces you to experience moments sequentially rather than all at once. And mass, through E equals mc squared, is intimately connected to the speed of light. So who decided the speed of light? In a very real sense, the speed of light decided who you are. It determined that you would be a temporal being, experiencing cause and effect, living moment to moment, unable to revisit the past or jump to the future. It determined the structure of atoms, the chemistry of life, the maximum rate at which your neurons can communicate, the delay between seeing something and perceiving it. Every aspect of your existence is shaped by this constant, and nobody decided it. It was built into the universe from the beginning. You didn't choose to be born into a universe with this speed of light, but you couldn't have been born into any other kind of universe. This is the only kind where beings like you can exist to ask the question. Before we move to the next section, take a moment. Look around you. Every photon hitting your eyes right now traveled at the speed of light to bring you information about the world. You're living inside a light cone, a bubble of causality defined by the cosmic speed limit. Everything you see, everyone you interact with, every thought you have, exists within this structure. The speed of light isn't separate from you. It's part of the fabric of your reality. An understanding that should fill you with awe. We've talked about what the speed of light is and why it matters. But let's dive into something that's equally fascinating. How do we actually measure it? And more importantly, why is measuring the speed of light one of the most technically challenging and conceptually intricate tasks in all of science? Because here's what will blow your mind. Every method we've ever used to measure the speed of light has depended on other measurements that themselves depend on the speed of light, creating a circular relationship that took centuries to untangle. Remember Ole Rachmer in 1676, timing the eclipses of Jupiter's moon Io? His method was brilliant but indirect. He wasn't measuring light traveling a known distance in a measured time. He was inferring the speed of light from discrepancies in astronomical observations. He had to assume he understood orbital mechanics perfectly, that his telescopes were accurate, that he was timing things correctly. His measurement was accurate to about 26%, which is impressive, but nowhere near modern precision. The first terrestrial measurement came from Hippolyte Fizeau in 1849 with his rotating toothed wheel. But think about what he needed to know. The exact distance to his mirror, 8,600 meters. How did he measure that? With surveying tools based on comparing lengths to a standard meter. But what defined a meter? At the time, it was defined as 1/10,000,000th of the distance from the North Pole to the equator along the Paris meridian. But how do you measure that distance accurately? You can see the circularity starting to creep in. Every measurement depends on other measurements. Leon Foucault improved on Fizeau's method in 1850 using a rotating mirror instead of a toothed wheel. His value was about 298,000 kilometers per second, much closer to the modern value. Albert Michelson spent much of his career refining the measurement. In 1879, he got 299,910 kilometers per second. By 1926, using better equipment and longer distances, he got 299,796 kilometers per second. He was getting incredibly close. But every refinement required better distance measurements, better time measurements, better equipment. And every piece of equipment, every measuring rod, every clock was itself subject to the physics that included the speed of light. Here's where things get really interesting. In the mid-20th century, physicists realized they could measure the speed of light more accurately by measuring frequency and wavelength of electromagnetic waves separately and multiplying them. The speed of light equals frequency times wavelength. By 1972, using lasers and extremely stable atomic clocks, scientists had measured the speed of light to an uncertainty of about 1 meter per second out of 300 million. That's 1 part in 300 million, incredibly precise. But they ran into a fundamental problem. The uncertainty in the measurement was dominated by the uncertainty in the definition of the meter. They could measure the speed of light more accurately than they could define what a meter was. So in 1983, the scientific community did something radical. They flipped the problem around. They said, we're defining the speed of light to be exactly 299,792,458 meters per second. Not approximately, exactly. And now we'll define the meter as the distance light travels in exactly 1/299,792,458th of a second. This wasn't arbitrary. They chose the number that best fit all existing measurements. But by making this definition, they turned the speed of light from a measurable quantity into a defined constant. You can't measure the speed of light anymore in the traditional sense. You can only measure distances and times, and the speed of light is the conversion factor between them, fixed by definition. Now, you might think this is cheating, that we're just defining away the problem. But it's actually the opposite. It's a recognition of something deep. The speed of light is more fundamental than our units of measurement. Meters and seconds are human inventions, arbitrary choices. The speed of light is a fundamental constant of nature. So it makes sense to base our measurement system on it rather than the other way around. And this isn't unique to the speed of light. We've done the same thing with other constants. The second is now defined based on the frequency of radiation from cesium atoms. The kilogram, as of 2019, is defined based on Planck's constant. We're building our entire measurement system on fundamental constants of nature, which is far more stable and universal than basing it on physical objects like prototag meters or kilograms that can change over time. But here's a question that should make you think. If we've defined the speed of light to be exact, how do we test whether it's really constant? How would we ever know if it changed? The answer is, we look for consistency across different measurements and different methods. If the speed of light changed, we'd see inconsistencies. Different physical laws that depend on the speed of light would give contradictory results. For example, the fine structure constant depends on the speed of light. If the speed of light changed, the fine structure constant would change, and that would affect atomic spectra in characteristic ways we could detect. We've looked for these changes by analyzing light from distant quasars, and we haven't found any. The speed of light, as far as we can tell, has been constant across billions of years of cosmic history. We've also tested whether the speed of light depends on the motion of the source or the observer. This was one of the key tests of special relativity. If light traveled at a fixed speed relative to its source, like sound traveling through air, then light from a moving source should be measured at different speeds by different observers. But every experiment, from Michelson-Morley to modern tests with particles in accelerators, confirms that the speed of light is the same regardless of the motion of source or observer. This is the principle of relativity, and it's been tested to extraordinary precision. We've tested it with light, with radio waves, with gamma rays, with particles moving at 99.9999% the speed of light in particle colliders. Always the same answer. The cosmic speed limit holds. There's something philosophically profound here. We can only understand the universe through measurement, but measurement requires units, and units are defined in terms of constants we've measured. There's an inescapable circularity. We can't step outside the universe to measure it with independent tools. We're inside the system, using the system to measure itself. The best we can do is check for internal consistency, making sure all our measurements and theories agree with each other. And remarkably, they do, at least within our current level of precision. The speed of light, along with a handful of other fundamental constants like Planck's constant, the gravitational constant, and the electron charge, forms a consistent framework within which we can understand the universe. Change any one of these constants, and the whole structure would collapse into contradiction. Here's what's amazing. Despite the circularity, despite the fact that we're using the universe to measure itself, we've achieved incredible precision. We can measure distances using laser interferometry to precisions of better than 1/1000th of a meter. We can measure time using atomic clocks to precisions of better than 1/1000th of a second. These capabilities have practical applications. GPS satellites, for example, depend on extremely precise time measurements. The satellites have atomic clocks that must be synchronized to nanosecond precision because they're calculating distances by measuring how long signals take to travel at the speed of light. General relativity predicts that clocks on satellites, moving relative to Earth's surface and experiencing weaker gravity, run at different rates than clocks on the ground. The difference is tiny, about 38 microseconds per day, but if you don't correct for it, your GPS location would be off by kilometers. The fact that GPS works, that you can navigate to within meters anywhere on Earth, is a daily, practical confirmation that our understanding of the speed of light and relativity is correct. So measuring the speed of light is no longer about finding a number. It's about testing the consistency and structure of physical law. It's about pushing the precision of our measurements to find any tiny discrepancy that might point to new physics. And that brings us to an exciting frontier. Are there any hints, any anomalies, any strange observations that suggest the speed of light might not be exactly constant in all situations? Let's explore that next. Science thrives on anomalies, on observations that don't quite fit our theories. And while the constancy of the speed of light is one of the most well-established facts in physics, there are some weird observations, some edge cases, some speculative ideas that make you wonder, is there more to the story? Could there be situations where the speed of light isn't quite what we think? Let's dive into the strange and the controversial, because this is where the next breakthroughs might come from. First, let's talk about something called vacuum birefringence. In quantum field theory, a vacuum isn't empty. It's a seething foam of virtual particles, constantly popping into and out of existence. These fluctuations can, in principle, interact with light passing through. In extremely strong magnetic fields, like those near magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's, a vacuum can become birefringent, meaning light of different polarizations travels at slightly different speeds. This effect is incredibly tiny, but it's been predicted by quantum electrodynamics, and there's some observational evidence for it from light coming from magnetars. If this is real, and most physicists think it is, then the speed of light in a vacuum isn't perfectly constant. It depends on the properties of the quantum vacuum, which can be affected by strong fields. Now, this doesn't violate relativity because the underlying maximum speed is still the same. It's just that the effective speed for light propagating through a region with quantum vacuum effects is slightly different. But it's a subtle point, and it shows that the vacuum is more complex than we once thought. Second, there's the cosmological question. Has the speed of light changed over the history of the universe? Some physicists, notably João Magueio and John Moffat, have proposed varying speed of light theories as alternatives to inflation for explaining the uniformity of the cosmic microwave background. The idea is that in the very early universe, shortly after the Big Bang, the speed of light might have been much higher, allowing distant regions to come into thermal equilibrium before the speed decreased to its current value. These theories are controversial. They require rethinking a lot of well-established physics. But they're not crazy. They're attempts to solve real problems, and they make testable predictions. So far, observations haven't supported them. The cosmic microwave background, the abundances of light elements from Big Bang nucleosynthesis, the distribution of galaxies, all of these are consistent with a constant speed of light and inflation. But the varying speed of light theories aren't ruled out entirely. There's still room for subtle variations that we haven't detected yet. Third, let's talk about something truly weird: quantum vacuum fluctuations and the Casimir effect. If you place two uncharged metal plates very close together in a vacuum, quantum fluctuations create a measurable force pushing the plates together. This is the Casimir effect, and it's been experimentally confirmed. The force arises because the quantum vacuum between the plates has different properties than the vacuum outside. Fewer virtual particles can fit in the gap, creating a pressure difference. Now, here's the wild part. Some theoretical work suggests that these vacuum effects could, in principle, be engineered to create regions where the speed of light is effectively different. This ties into ideas about warp drives and traversable wormholes, which require exotic matter with negative energy density. The Casimir effect gives us negative energy density, but only in tiny amounts and under specific conditions. Could we scale this up? Could we create macroscopic regions where spacetime has different properties? It's wildly speculative, but it's not forbidden by known physics. It's just incredibly difficult and might be practically impossible. But the fact that it's even conceivable shows how much we still have to learn. Fourth, There are observations from high-energy astrophysics that hint at something strange. When a distant gamma-ray burst occurs, it emits photons of different energies. These photons travel billions of light years through space to reach us. If the vacuum has quantum foam structure at the Planck scale, high-energy photons might interact with it differently than low-energy photons, causing them to travel at slightly different speeds. The differences would be incredibly tiny, but over billions of light years, they might add up to measurable delays. Some observations have suggested such delays, but they're controversial. Other observations haven't found them. It's possible the delays are due to astrophysical effects at the source rather than fundamental physics. Or maybe there really is Planck scale structure affecting light. We need more data. This is an active area of research, and future observatories with better sensitivity might settle the question. Fifth, and this is more philosophical, there's the question of whether the speed of light is truly fundamental or emergent. In some approaches to quantum gravity, like loop quantum gravity or certain string theory models, spacetime itself is emergent from something more fundamental, perhaps a network of quantum information or relationships. If spacetime is emergent, then the speed of light, which is a property of spacetime, is also emergent. It arises from deeper principles. But what are those principles? And could they allow for situations where the effective speed of light is different? For example, in some models, spacetime might have a discrete structure at the Planck scale, like pixels on a screen. Light propagating through discrete spacetime might behave differently than light propagating through continuous spacetime. It might have dispersion, meaning different frequencies travel at slightly different speeds. These effects would be tiny at everyday scales, but might be detectable in high-energy astrophysics. Now, let's be clear. None of these ideas have overturned the standard understanding of the speed of light. The constancy of the speed of light in a vacuum remains one of the best-tested principles in physics. But these anomalies and speculations remind us that science is never finished. There are always edges to explore, always questions that don't have definitive answers yet. And that's exciting. That's where discovery happens. Here's another angle. Could there be particles that travel faster than light? We've talked about how nothing with mass can reach the speed of light. But what about particles with imaginary mass? In the 1960s, physicists speculated about hypothetical particles called tachyons that would travel faster than light. If tachyons exist, they would have bizarre properties. They would lose energy as they sped up and gain energy as they slowed down. They would violate causality, potentially allowing information to travel backward in time. Most physicists think tachyons don't exist because we've never observed them and because they would create causality paradoxes. But interestingly, tachyons appear in some formulations of string theory as unstable modes. The presence of tachyons in a theory usually signals that the theory is in an unstable vacuum state and will decay to a more stable configuration where tachyons don't exist. So even in theories where tachyons appear mathematically, they're a sign of instability, not real physical particles. But here's a twist. There are phenomena that seem to move faster than light, but don't actually transmit information or energy faster than light. For example, if you shine a laser pointer at the moon and sweep it across the lunar surface, the spot can move faster than light. If you move your hand 1 degree in 1 second, the spot moves about 6,700 kilometers in 1 second, more than 20 times the speed of light. But no information is traveling faster than light. Each photon is still traveling at the speed of light from your pointer to the moon. The spot is just a series of different photons hitting different locations. Nothing physical is moving along the surface faster than light. Similarly, phase velocities in certain materials can exceed the speed of light. The phase of a wave, the peak of the oscillation, can move faster than light. But the group velocity, the speed at which the envelope of the wave and its information content moves, never exceeds the speed of light. Nature has these clever ways of allowing apparent, faster-than-light phenomena without actually violating causality. All of this brings us to a humbling realization. The speed of light is both the most precisely measured constant in physics and one of the most mysterious. We know what it is. We know how it behaves. We can measure it to extraordinary precision. But we don't fully know why it is what it is, whether it's truly fundamental or emergent, or whether there are subtle contexts where it behaves differently than we expect. And that's okay. That's the nature of science. We build increasingly accurate models, but there's always another layer of understanding waiting to be uncovered. And the speed of light sits at the center of many of these deep questions. Now let's step back from the equations and experiments and ask, what does the speed of light tell us about the nature of reality itself? Because once you truly understand what the cosmic speed limit means, it forces you to confront some of the deepest philosophical questions humans have ever asked. What is time? What is causality? Is the universe deterministic or open? And perhaps most unsettling, is free will even possible in a universe governed by the speed of light? Let's start with the block universe, a concept that emerges directly from Einstein's relativity. If the speed of light is constant for all observers, and simultaneity is relative, then there's no universal present moment. Different observers moving at different speeds will disagree about which events are happening now. So what does now even mean? One interpretation, favored by many physicists, is that the past, present, and future all exist equally. The universe is a four-dimensional block of space-time, and time is just another dimension like the spatial dimensions. Your life is a world line, a path through this block, and all moments of your life exist eternally in the block universe. You moving through time is like a character in a book, existing across multiple pages. All the pages exist simultaneously, even though the character experiences them sequentially. Think about what this means for your experience right now. If the block universe is real, then every moment of your past still exists somewhere in space-time. Your childhood, your first memory, every embarrassment and triumph, they're all still there, frozen in the structure of space-time. And your future, every decision you'll make, every experience you'll have, already exists too. You just haven't reached those pages yet. From the perspective of a being that could perceive all of space-time at once, a being outside time, your entire life from birth to death would be visible as a single four-dimensional object, a static pattern in space-time. Nothing changes from that perspective. Change is an illusion that emerges from our limited, time-bound perspective, moving along our world line at 1 second per second. This idea should be deeply unsettling. It suggests that the future is already determined, already existing, just waiting for you to experience it. Where's the room for choice? Where's the room for free will? And here's where the speed of light comes in. The cosmic speed limit creates the structure of causality that might preserve some notion of free will. Even in the block universe, there's a distinction between your past light cone, events that could have influenced you, and your future light cone, events you could potentially influence. Events outside your light cone are causally disconnected from you. They can't affect you, and you can't affect them. This creates a kind of causal structure where your choices, whatever they are, can genuinely affect what happens in your future light cone without being predetermined by events outside your past light cone. But here's the problem. If all of space-time exists as a block, then the events in your future light cone already exist. Your choices are already made, already part of the structure, even if you haven't experienced making them yet. The philosopher and physicist view this differently. Some philosophers argue that this is compatible with free will, because your choices are still your choices. They're just eternally part of the structure. The fact that they exist at all space-time coordinates doesn't mean they weren't freely chosen. They're freely chosen events that happen to exist timelessly. Other philosophers argue this is incompatible with any meaningful notion of free will. If your choice tomorrow already exists in the block universe, in what sense is it free? Now let me make this even more complicated. Quantum mechanics throws a wrench into the block universe picture. In quantum mechanics, the future isn't determined. The wave function describes probabilities, not certainties. When you measure a quantum system, the wave function collapses to one of many possible outcomes. The outcome is genuinely random, or at least appears to be from our perspective. If quantum randomness is fundamental, then the future isn't fixed. The block universe might be a block up to the present, but the future is open, probabilistic, branching into multiple possible timelines. Or, in the many worlds interpretation, all possible quantum outcomes actually occur, creating a vast branching structure of parallel universes. The block universe becomes a branching multiverse, and the speed of light defines the causal structure within each branch. How does the speed of light relate to this? In quantum field theory, the speed of light is the maximum speed at which quantum information can propagate. When a wave function collapses, the collapse doesn't spread faster than light. This is important for maintaining causality. If wave function collapse could propagate faster than light, you could use it to send information to your own past in some reference frames, creating paradoxes. The speed of light protects the consistency of quantum mechanics and relativity together. Let's shift gears and talk about the arrow of time. Why does time flow forward? Why do we remember the past, but not the future? Why do eggs break, but not unbreak? Why does entropy increase? These are all aspects of the arrow of time, and they're deeply connected to the speed of light. The second law of thermodynamics says entropy, roughly disorder, always increases in closed systems. But the fundamental laws of physics are time-symmetric. If you watch a video of particles bouncing off each other at the microscopic level, you can't tell if the video is playing forward or backward. Both directions obey the laws of physics. So why does the universe have an arrow of time at the macroscopic level? The answer seems to be initial conditions. The universe started in a very low entropy state at the Big Bang, highly ordered, and entropy has been increasing ever since. But why did it start that way? We don't know. This is one of the deepest mysteries in cosmology. And the speed of light is intimately connected because the structure of space-time, determined by the speed of light, is what allows entropy to increase in a directional way. The expansion of the universe, the flow of energy from concentrated sources like stars into diffuse backgrounds, the irreversible processes of thermodynamics, all of these depend on the causal structure of spacetime, which is defined by the cosmic speed limit. Here's another philosophical angle. The speed of light creates a horizon, a boundary to what we can know. Because information can only travel at the speed of light, and the universe is only about 13.8 billion years old, we can only see a finite region of space, about 46 billion light years in radius, accounting for expansion. Beyond that is the cosmological horizon. There could be infinite space beyond what we can see, but we'll never know. The speed of light creates a fundamental limit on knowledge, an epistemological horizon. We're trapped inside our observable bubble, forever unable to know what lies beyond. And as the universe expands, this horizon doesn't grow to encompass more. It actually shrinks in terms of the number of galaxies we can see. Distant galaxies are receding from us due to the expansion of space, and as they cross the cosmological horizon, they disappear from view. Their light can no longer reach us. The universe is becoming more unknowable over time. Future civilizations will have less evidence about the structure and history of the cosmos than we do. The speed of light and cosmic expansion are conspiring to hide information, to create isolated bubbles of causality that can never communicate. This is called cosmic censorship, and it's both a practical limitation and a philosophical statement about the nature of reality. Now, let's talk about something even more mind-bending, the holographic principle. This is an idea from theoretical physics, particularly string theory and quantum gravity, that suggests the information content of a region of space is proportional to its surface area, not its volume. Think about that. The amount of information inside a sphere is limited by the area of the sphere's surface, not the volume it encloses. This is weird. It suggests that our three-dimensional reality might be a projection, a hologram, of information encoded on a two-dimensional surface. And the speed of light is central to this idea because it defines the maximum rate at which information can be transferred, and it relates to the entropy bounds that lead to the holographic principle. The connection comes from black hole thermodynamics. Black holes have entropy proportional to their surface area, not their volume. This was discovered by Jacob Bekenstein and Stephen Hawking in the 1970s. And the entropy is related to the amount of information the black hole contains. When matter falls into a black hole, the information about that matter is somehow encoded on the black hole's event horizon. This led to the holographic principle. Maybe all of spacetime works this way. Maybe the three-dimensional universe we experience is a holographic projection of information encoded on a distant two-dimensional surface. If this is true, then the speed of light isn't just a speed limit. It's related to the fundamental resolution of reality, the rate at which information can be processed by the holographic screen. This is speculative, but it's based on serious theoretical work. And if it's true, it would mean reality is even stranger than we imagined. You, your thoughts, your experiences, everything you see and touch would be a holographic projection, emergent from information encoded somewhere else. The speed of light would be part of the projection mechanism, the rate at which the hologram updates and maintains consistency. Here's one more philosophical implication. The speed of light creates a fundamental loneliness in the universe. Because of the cosmic speed limit and the vast distances between stars and galaxies, meaningful communication with other civilizations, if they exist, might be effectively impossible. The nearest star system is 4.2 light-years away. A round-trip message would take over 8 years. The nearest star that might have an Earth-like planet is further. A conversation would take decades. For galaxies beyond our local group, the expansion of space makes communication impossible even in principle. Any civilization in a distant galaxy is forever beyond our reach. We're isolated by the cosmic speed limit, alone on our tiny world, gazing out at a universe we can observe, but never truly touch. This should make you feel something. The speed of light isn't just a number. It's a statement about the structure of existence, about what's possible and what's forever out of reach. It determines the boundaries of knowledge, the nature of causality, the flow of time, possibly even the reality of free will. Nobody decided the speed of light, but whoever or whatever determined the fundamental structure of the universe when it was born made a choice or set an initial condition that ripples through every aspect of reality. And we're here, conscious beings made of atoms, experiencing this reality one moment at a time, trying to understand the rules that govern us. Before we move on, I want you to take a moment and think about your own existence in light of everything we've discussed. You are a pattern of atoms, held together by electromagnetic forces that propagate at the speed of light. Your thoughts are electrical impulses traveling through neurons. Your perception of reality is constructed from photons that traveled at the speed of light to reach your eyes. You're embedded in a causal structure defined by the cosmic speed limit. And yet you feel like a unified, continuous self, making choices, experiencing time, interacting with the world. The speed of light is so fundamental that you can't escape it, but it's so invisible that you never think about it. Until now. Let's bring this down to Earth for a moment, literally, because the speed of light isn't just an abstract cosmic principle. It's the foundation for countless technologies you use every day, often without realizing it. Your smartphone, your internet connection, GPS navigation, medical imaging, our understanding of chemistry and materials. All of it depends on our knowledge of the speed of light and the physics that comes from it. Let's explore how this cosmic constant has been harnessed to change human civilization. Start with fiber optic communication. Right now, As you're watching or listening to this, if you're streaming it over the internet, the data is probably traveling through fiber optic cables as pulses of light. Fiber optics work by sending light through thin glass fibers using total internal reflection. The light bounces off the walls of the fiber without escaping, traveling long distances with minimal loss. Modern fiber optic networks can transmit data at speeds of hundreds of terabits per second, and they're limited primarily by the speed of light in glass, which is about 2/3 the speed of light in vacuum. The entire global internet, the infrastructure that connects billions of people, depends on our ability to manipulate light and our understanding of how fast it travels. Think about undersea cables connecting continents. There are hundreds of these cables crisscrossing the ocean floors, each containing multiple fiber optic strands. A message from New York to London travels through these cables at about 2/3 the speed of light, covering the roughly 5,500 kilometers in about 28 milliseconds. That's one way. The round trip, including processing time, might be 50 to 100 milliseconds. This latency matters for everything from financial trading, where milliseconds can mean millions of dollars, to video calls, where delays make conversation awkward. The speed of light is the ultimate bottleneck in global communication. GPS is another technology that completely depends on precise knowledge of the speed of light. GPS satellites orbit about 20,000 kilometers above Earth, each carrying atomic clocks synchronized to nanosecond precision. When your phone calculates its position, it receives signals from multiple satellites. Each signal contains a timestamp of when it was sent. Your phone knows what time it is locally, so by comparing timestamps, it can calculate how long each signal took to travel from satellite to phone. Since the signals travel at the speed of light, distance equals the speed of light times travel time. By knowing the distance to at least 4 satellites and the satellites' positions, your phone can triangulate your exact location. If the speed of light were different, or if we didn't know it precisely, GPS wouldn't work. But here's the really cool part. GPS has to account for both special and general relativity. The satellites are moving at about 14,000 kilometers per hour relative to Earth's surface, which causes time dilation, making their clocks run slower by about 7 microseconds per day. But they're also in weaker gravity than at Earth's surface, which causes their clocks to run faster by about 45 microseconds per day due to general relativistic time dilation. The net effect is about 38 microseconds per day faster. If we didn't correct for this, GPS would accumulate errors of about 10 kilometers per day. The fact that GPS works is a daily confirmation that relativity is real, that our understanding of the speed of light and spacetime is correct. Millions of people use GPS every day without realizing they're relying on Einstein's theories from over 100 years ago. Medical imaging also depends on the speed of light. PET scans, positron emission tomography, work by detecting gamma rays produced when positrons from radioactive tracers annihilate with electrons in your body. The gamma rays travel at the speed of light, and by detecting them with sensors around your body and measuring precisely when they arrive, computers can reconstruct 3-dimensional images of metabolic activity in your organs. This allows doctors to detect cancer, brain disorders, heart disease. The precision of these images depends on knowing exactly how fast light travels and how to account for it in the reconstruction algorithms. Spectroscopy, the analysis of light to determine what things are made of, is foundational to chemistry, astronomy, environmental science, and materials engineering. Every element and molecule absorbs and emits light at characteristic wavelengths. By analyzing the spectrum of light from a substance, we can identify what it contains. This works because electrons and atoms can only exist at specific energy levels, and when they jump between levels, they emit or absorb photons with energies corresponding to the energy difference. The energy of a photon is related to its frequency by Planck's constant, and the frequency is related to wavelength by the speed of light. So the speed of light is literally the conversion factor that lets us translate observed wavelengths into energies, and thus into atomic and molecular identities. Every lab analyzing materials, every telescope analyzing starlight, every environmental monitor checking air quality, they're all using spectroscopy, which depends on the speed of light. Astronomy and cosmology are entirely built on the speed of light. When we observe distant galaxies, we measure their light's wavelength and intensity. The wavelength tells us how fast the galaxy is moving away from us due to the expansion of space, the redshift. The intensity tells us how far away it is. Combined with knowledge of the intrinsic brightness of certain standard candles, like Type Ia supernova or Cepheid variable stars. All of this depends on light traveling at a known, constant speed. The entire cosmic distance ladder, the series of methods we use to measure distances from nearby stars to the most distant galaxies, relies on the speed of light being constant. If it weren't, cosmology would collapse. Quantum computing, one of the most cutting-edge technologies being developed today, also depends on understanding light and quantum mechanics. Many quantum computers use photons as qubits because photons don't interact with their environment as much as massive particles, which helps maintain quantum coherence. Manipulating photons at the quantum level requires precise control of light's properties, including its speed in different materials, its polarization, its quantum states. As we develop quantum internet and quantum cryptography, systems where quantum information is transmitted via photons through fiber optics, the speed of light will be the bandwidth limit, the maximum rate at which quantum information can be shared. Even something as everyday as lighting has been revolutionized by our understanding of light. LED lights, which are now replacing incandescent bulbs worldwide, work because of quantum mechanics. An LED is a semiconductor device where electrons recombine with holes, releasing energy as photons. The color of the light depends on the energy gap in the semiconductor, which depends on its atomic structure and quantum mechanical properties. Designing efficient LEDs require deep understanding of how electrons and photons interact, which ultimately comes down to quantum electrodynamics, the theory of light and matter interaction that includes the speed of light as a fundamental constant. Solar panels, which convert light into electricity, also depend on quantum mechanics and our understanding of light. Photons hit the semiconductor material in the panel, transferring their energy to electrons and creating an electrical current. The efficiency of this process depends on matching the photon energies to the band gap of the semiconductor. Again, this is quantum mechanics in action, and the speed of light is part of the relationship between photon energy and wavelength. Let's talk about something more speculative, but incredibly exciting: laser propulsion for spacecraft. Traditional rockets carry their fuel with them, which makes them heavy and limits their speed. But what if we could push spacecraft with lasers from Earth, or from space-based platforms? The photons from the laser carry momentum, and when they hit a reflective sail on the spacecraft, they transfer that momentum, accelerating the craft. This is called photon propulsion or laser sailing. The Breakthrough Starshot Initiative is planning to use powerful Earth-based lasers to accelerate tiny spacecraft to about 20% the speed of light, fast enough to reach the nearest star system in about 20 years. This only works because we understand precisely how light carries momentum, how fast it travels, and how to generate and direct enormous amounts of light power. If successful, this would be humanity's first interstellar probe, and it's fundamentally based on the properties of light. Here's something to consider. Almost every major technology of the modern world, from computers to telecommunications, to medicine to energy, either directly uses light or depends on physics that comes from understanding the speed of light and relativity. The 20th century was the century of the speed of light. Relativity and quantum mechanics, both intimately connected to the cosmic speed limit, gave us transistors, lasers, nuclear power, particle physics, cosmology, GPS, the internet, medical imaging, and so much more. The 21st century is continuing this revolution with quantum technologies, advanced materials, space exploration, and AI-driven science. And all of it traces back to asking, how fast does light travel? And what does that tell us about the universe? The speed of light has gone from a curious question in natural philosophy to the foundation of modern civilization. Nobody decided it. Nature decided it. But humans decided to understand it, to measure it, to build upon it, to harness it. And in doing so, we've transformed our species and our relationship to the cosmos. So where do we go from here? We've measured the speed of light to extraordinary precision. We've built technologies upon it. We've tested relativity in countless ways. But science never stops. There are new frontiers opening up, new questions emerging, and new ways the speed of light will shape humanity's future. Let's explore what's coming next. First, the search for quantum gravity. This is the holy grail of theoretical physics right now. A theory that unifies quantum mechanics and general relativity, that can describe gravity at the smallest scales and highest energies. String theory, loop quantum gravity, causal set theory, asymptotic safety, there are multiple approaches, but none are confirmed yet. And any successful theory will have to say something about the speed of light at the most fundamental level. Is it truly a constant, or does it emerge from something deeper? Does it behave differently at the Planck scale, the smallest scale where quantum gravity effects become important? One approach to testing this is through ultra-high energy astrophysics. When cosmic rays, the highest energy particles in the universe, hit Earth's atmosphere, they create showers of particles. Some of these particles have energies so high that they shouldn't even be able to travel cosmic distances, according to current theory. They should lose energy by interacting with the cosmic microwave background, but we detect them anyway. This is the GZK paradox, named after Greisen, Zhatzman, and Kuzmin, who predicted the cutoff. Why are we seeing these ultra-high energy particles? Is it a violation of Lorentz invariance, the principle that the laws of physics are the same for all observers, which is intimately connected to the constancy of the speed of light? Or is there astrophysics we don't understand? Experiments like the Pier Auger Observatory are gathering more data, and the answer will tell us something fundamental about the structure of spacetime. Second, gravitational wave astronomy is opening a completely new window on the universe. In 2015, LIGO detected gravitational waves from merging black holes for the first time. Gravitational waves are ripples in spacetime itself, predicted by Einstein's general relativity. They travel at the speed of light, not faster, not slower, exactly at the speed of light. This is a prediction of general relativity. Gravity and electromagnetic radiation propagate at the same speed because they're both properties of spacetime. Testing this has profound implications. In 2017, when LIGO and Virgo detected gravitational waves from merging neutron stars, and telescopes around the world detected the light from the same event, the gravitational waves and the light arrived within seconds of each other after traveling over 100 million light years. This confirmed that the speed of gravitational waves equals the speed of light to 1 part in 10 to the 15th. That's an incredible constraint on any theory of gravity. Future gravitational wave detectors, like the space-based LISA mission planned for the 2030s, will detect waves from supermassive black holes merging from the early universe, possibly even from cosmic strings or other exotic phenomena. These observations will test general relativity in extreme conditions and might reveal deviations that point to quantum gravity. And all of these tests are fundamentally about the speed of light, or more precisely, the speed of causality that both light and gravity obey. Third, quantum communication and quantum internet are coming. Companies and research institutions are already building prototype quantum networks where information is transmitted via entangled photons. These networks could enable unhackable communication because any attempt to intercept the quantum information would disturb it in a detectable way. They could also enable distributed quantum computing, where quantum processors in different locations work together on problems. The speed of light will be the ultimate latency limit for these quantum networks. You can't have instantaneous quantum entanglement communication. You still need classical signals to compare measurement results. But within the light speed limit, quantum networks will revolutionize information security and computing. China has already launched a quantum communication satellite, demonstrating quantum key distribution over thousands of kilometers. This is the beginning of a quantum information age, and the speed of light is the framework within which it operates. Fourth, advances in metamaterials and photonics are giving us unprecedented control over light. Metamaterials are engineered structures with properties not found in nature. They can bend light in unusual ways, creating effects like negative refraction, cloaking, and superlensing that breaks the diffraction limit. Some metamaterials can slow light down dramatically, or even bring it to a halt, storing light energy in collective excitations of the material. While light in a vacuum always travels at the speed of light, light in carefully designed materials can be controlled with exquisite precision. This has applications in optical computing, where information is processed using light instead of electrons, potentially enabling computers much faster than current electronic ones, because light can carry more information and doesn't heat up wires the way electric current does. The speed of light becomes an advantage rather than a limit in optical computing. Fifth, space exploration is entering a new era, and the speed of light is both an enabler and a barrier. We're planning missions to Mars, potentially crewed missions in the 2030s. Communication with Mars has a light time delay ranging from about 3 minutes when Mars is closest to Earth to 22 minutes when it's farthest. This means conversations are impossible. Everything has to be asynchronous messages. For missions to the outer solar system, the delays are even longer. A signal from Voyager 1, now in interstellar space over 24 billion kilometers away, takes over 22 hours to reach Earth. As we explore further, we'll push against the light speed barrier more and more. Any future crewed mission to another star would face delays measured in years, making real-time control from Earth impossible. Interstellar probes will have to be autonomous, making decisions on their own, because waiting for instructions from home isn't feasible. The dream of interstellar travel faces the speed of light as its greatest challenge. Even at 10% the speed of light, which is far beyond our current capabilities, the nearest star would take over 40 years to reach. At 1% the speed of light, which might be achievable with nuclear pulse propulsion or laser sails, it would take over 400 years. The human lifespan is a problem. Generation ships, where multiple generations live and die during the journey, suspended animation, digital uploads of consciousness. These are the kind of solutions science fiction explores, but they're serious considerations if we ever want to reach the stars. The speed of light might confine humanity to our solar system indefinitely, or it might force us to fundamentally change what it means to be human in order to cross interstellar distances. Sixth, artificial intelligence and computing are approaching interesting limits related to the speed of light. As processors get faster and more densely packed, the time it takes for signals to travel between components becomes a bottleneck. Light travels about 30 centimeters in 1 nanosecond. If a processor is operating at gigahertz speeds, billions of operations per second, signals can only travel tens of centimeters in 1 clock cycle. This is why modern CPUs and GPUs have multiple cores close together, why cache memory is physically near processing units, why there's so much work on reducing latency. The speed of light is becoming a practical limit on computing architecture. Future computers might need to be three-dimensional, stacking components vertically to minimize distances, or they might need to operate at lower clock speeds with more parallelism. Or we might transition to optical or quantum computing paradigms where information is processed differently. Seventh, our understanding of cosmology is evolving. The James Webb Space Telescope is showing us galaxies as they were over 13 billion years ago, less than 700 million years after the Big Bang. We're seeing the first stars and galaxies forming, testing our theories of cosmic evolution. Future telescopes might see even further back, closer to the Big Bang itself. But there's a limit: the cosmic microwave background, the light emitted about 380,000 years after the Big Bang, when the universe became transparent. Before that, the universe was opaque to light. We can't see earlier with light, but we might be able to see with gravitational waves or with neutrinos, which decouple from matter earlier. The speed of light defines one horizon for observation, but other messengers might let us see beyond it. And there's dark energy, the mysterious force causing the expansion of the universe to accelerate. We don't know what it is. It makes up about 68% of the universe's energy content, but we can only detect it through its gravitational effects on expansion. Understanding dark energy is one of the biggest questions in physics. And interestingly, the speed of light plays a role. If the dark energy density were different, the expansion history would be different, changing the light travel times and distances to distant galaxies. Measuring these precisely lets us constrain what dark energy could be. The speed of light is our measuring stick for the universe's expansion. Here's the big picture. Humanity is in a phase of explosive growth in knowledge and capability, and the speed of light is central to almost every frontier we're pushing. From the smallest scales of quantum gravity to the largest scales of cosmology, from the most practical technologies to the most speculative ideas about the future, the cosmic speed limit shapes what's possible. We didn't decide it, but we're learning to work within it, to understand it more deeply, and to use it as a tool for exploration and creation. And maybe, just maybe, there are discoveries waiting that will change our understanding of the speed of light itself. Maybe there's a loophole, a way to sidestep the limit without violating causality. Maybe wormholes are possible, connecting distant parts of space without requiring faster-than-light travel. Maybe the multiverse is real, and there are other universes with different speeds of light, some of which might permit technologies we can't imagine. Or maybe the speed of light is truly absolute, an unbreakable law, and humanity's future is to explore and settle our own galaxy over millions of years, accepting that the universe is vast and we are small, but that there's still wonder and discovery enough to occupy us for eternity. We're in the home stretch now, and I want to bring this back to you one more time, but at a deeper level than before. Because here's what I want you to understand. The speed of light isn't just a fact about the universe out there. It's a fact about you, your existence, your perception, your place in the cosmos. And recognizing that can genuinely change how you experience being alive. Let's start with scale. You are made of atoms, about 7 billion atoms. Each atom is held together by electromagnetic forces mediated by photons. Virtual photons constantly being exchanged between electrons and nuclei at the speed of light. Your very structural integrity depends on the cosmic speed limit. But you're not just atoms. You're a pattern, an arrangement of atoms that somehow gives rise to consciousness, to subjective experience, to the sense that there's someone home. Are you experiencing the world? How does that happen? We don't fully know. It's the hard problem of consciousness. But we do know that it depends on information processing in your brain, on neurons firing, on electrochemical signals propagating, on patterns of activity that encode thoughts and memories and feelings. And all of this happens at speeds far below the speed of light, but within the framework set by it. Your perception of now, this moment, is actually a construction. Your brain takes sensory inputs that arrived at slightly different times, processes them through multiple stages of neural circuitry, each taking time, and then assembles them into a coherent experience that you perceive as happening now. But that now is actually somewhere between 50 to 500 milliseconds in the past, depending on the stimulus and the processing required. You're living slightly in the past, Always, because your brain needs time to construct your experience. And the information your brain is working with arrived via light, sound, touch, all limited by the speed of propagation. The speed of light is the ultimate limit, but your neural processing is the practical limit. You experience the world through a filter of delays and constructions, and what you perceive as reality is a model your brain creates, not reality itself. This should be humbling. You don't have direct access to the world. You have access to your brain's reconstruction of signals that represent the world. And those signals are always old, always delayed by the time it took them to propagate. Even the sense of your own body, proprioception, involves signals traveling from sensors in your muscles and joints up your spinal cord to your brain. For your toes, that's about a meter of nerve fiber, and signals travel at around 50 to 100 meters per second. So there's a 10 to 20 millisecond delay between something happening to your toe and you becoming aware of it. You're piloting your body with a delay, reacting to information that's already out of date. It's amazing you function as well as you do. Now think about your relationships, your connections with other people. Every interaction you have involves signals propagating at finite speeds. When you talk to someone, your words are sound waves traveling at 343 meters per second. When you look at them, the light from their face travels at the speed of light to your eyes. When you touch them, mechanical pressure propagates through your skin and theirs at the speed of sound in tissue. Every connection is mediated, delayed, indirect. You never truly touch another person's experience. You only perceive signals from them, interpret those signals, and respond with signals of your own. There's a fundamental isolation, a separateness, imposed by the finite speed of information transfer. And yet, despite this isolation, you form bonds. You love people. You communicate meaning, share experiences, create relationships that feel immediate and direct, even though they're technically mediated by these physical processes. This is both beautiful and strange. The human experience transcends the physical limitations in a sense, creating subjective feelings of connection and presence that go beyond the mere exchange of signals. But it's also constrained by the physical. Long-distance relationships are harder, partly because of distance, but also because of latency. Video calls with even a few hundred milliseconds of delay feel awkward because the natural rhythm of conversation is disrupted. The speed of light becomes a felt presence in your relationships when the distances are large enough. Let's zoom out. You exist at one moment in the history of the universe, one brief flicker in a span of billions of years. The light you see from distant stars is ancient, showing you the universe as it was in the past. You're surrounded by history, by ghosts of light that have been traveling for thousands of millions or billions of years to reach you. When you look at the Andromeda Galaxy, you're seeing it as it was 2.5 million years ago. Your ancestors, early humans, were just beginning to use stone tools when that light left Andromeda. It's traveled all that time just to hit your retina tonight. There's something profound in that. You're connected to the deep pass through light, through the cosmic speed limit that makes light a messenger carrying information across time and space. And you're connected to the future too, in a way. The light leaving Earth right now will travel outward, carrying information about this moment, about our civilization, about you in some infinitesimally small way into the cosmos. In 1,000 years, that light will be 1,000 light years away. In 1,000,000 years, 1,000,000 light years away. Long after you're gone, long after humanity might be gone, that light will still be traveling, a faint echo of this moment spreading through the universe at the cosmic speed limit. You're part of the universe's light cone, part of the causal structure of spacetime, and your existence sends ripples outward that will propagate literally forever. Does that make you feel insignificant? It might. You're one person on one planet around one star in one galaxy, among hundreds of billions of galaxies. The universe is incomprehensibly vast, and you're a tiny part of it, existing for a cosmological instant. But here's the flip side. You're part of the universe, becoming aware of itself. You're a configuration of atoms that can contemplate atoms, a pattern of matter that can wonder about patterns, a localized structure that can grasp universal principles like the speed of light. In you, the universe has created something that can understand, at least partially, how it works. That's not insignificant. That's miraculous. The speed of light connects you to everything. The atoms in your body were forged in stars that exploded billions of years ago. The carbon, nitrogen, oxygen, iron, all the elements heavier than hydrogen and helium. They were created by nuclear fusion in stellar cores and scattered across space when those stars died. That stardust drifted through space, eventually coalescing into the cloud that formed our solar system, the Earth, and eventually you. The light from those ancient stars traveled through space, and now you're made of the remnants. You are, quite literally, star stuff contemplating stars, as Carl Sagan famously said. And the cosmic speed limit is what allowed this to happen over billions of years, creating the timescales necessary for stellar evolution, for planets to form, for life to emerge and evolve. Think about consciousness itself. Whatever consciousness is, whether it's an emergent property of complex information processing or something more mysterious, it exists within you as a pattern of activity in your brain. That pattern persists through time, giving you a sense of continuity, a feeling that you're the same person you were yesterday and will be tomorrow. But physically, you're not the same. The atoms in your body are constantly being replaced through metabolism. Most of the atoms that were part of you a year ago aren't part of you anymore. What persists is the pattern, the information, the organization. And that pattern unfolds in time at speeds governed by chemistry and biology, which are ultimately governed by the electromagnetic interactions that propagate at the speed of light. Your memories are physical structures, patterns of strengthened synaptic connections in your brain. When you remember something, you're not accessing a recording. You're reconstructing the memory from these patterns. And each time you remember, you slightly change the memory. Your past is constantly being rewritten by your present. The person you are now is constructed from memories that are themselves constructions, all playing out in the causal structure of spacetime defined by the cosmic speed limit. You're a process, not a thing. You're a verb, not a noun. You're happening, unfolding moment by moment within the framework set by the laws of physics. Now let's talk about meaning. In a universe governed by physical laws, where does meaning come from? The speed of light doesn't care about you. The laws of physics are indifferent to human concerns. Atoms follow electromagnetic forces. Planets orbit stars according to gravity. Light travels at its cosmic speed limit. None of this has inherent meaning or purpose. It just is. And yet, you experience meaning. You value things, care about people, pursue goals, create art, ask questions, seek understanding. Where does that come from in a meaningless universe? The answer, I think, is that meaning isn't found. It's created. You create meaning through your choices, your relationships, your pursuits. The universe doesn't hand you a purpose, but it gives you the freedom to choose one. And in that freedom lies something profound. You're not a passive observer of a predetermined script. You're an active participant, making decisions that genuinely shape your future within the constraints of physical law. The speed of light sets limits on what's possible, but within those limits, there's vast room for creativity, for choice, for meaning-making. And here's something beautiful. Your ability to understand the speed of light, to grasp this cosmic principle that governs reality, is itself meaningful. Understanding is a form of connection, a way of relating to the universe. When you comprehend that light travels at a finite speed, that this speed determines the structure of causality and the flow of time, that it shapes everything from atoms to galaxies to your own perception, you're participating in something larger than yourself. You're part of humanity's collective effort to understand our place in the cosmos. Every scientist who contributed to this understanding, from Rackmer to Maxwell, to Einstein to Hawking, and countless others, they were all part of this grand project, and so are you by engaging with these ideas. There's also something to be said about acceptance and humility. The speed of light is a limit. There are places in the universe you will never be able to visit, events you will never be able to witness, questions you may never be able to answer. The universe is larger and older and stranger than you can fully comprehend. And that's okay. In fact, that's wonderful. It means there's always more to discover, always deeper layers of understanding to pursue. The universe isn't a problem to be solved and then filed away. It's an endless source of wonder and mystery. The speed of light reminds you of your limitations, but it also reveals the vastness of what's possible within those limitations. Let me share something personal. When I think about the speed of light, I think about connection and separation. I think about how we're all isolated islands of consciousness, separated by distance and delay, and yet we reach out to each other through signals, through language and art and touch, creating bridges across the gaps. I think about how the present moment is already gone by the time you perceive it, how we're all living slightly in our own past, and yet we synchronize our experiences well enough to function together. I think about how the light from distant stars has traveled for eons just to reach us, how we're receiving messages from the deep past with every glance at the night sky. And I think about how everything is connected through causality, through the light cones that link events across spacetime. The speed of light teaches you that you're part of something larger, something structured and lawful and comprehensible, at least partially. It teaches you that your existence is contingent on countless factors, from the values of fundamental constants to the history of the universe, to the specific circumstances of your birth. And it teaches you that despite all these constraints, despite the deterministic laws and the finite speeds and the cosmic isolation, you still have the capacity to wonder, to question, to understand, to create meaning. That's the human condition. Constrained but free, limited but creative, isolated but connected, temporary but significant. So when you look up at the night sky tonight, when you see the stars, remember that you're seeing ancient light, photons that have traveled for years or centuries or millennia at the cosmic speed limit to reach you. Remember that those photons are part of the causal structure of the universe, carrying information from the past into your present. Remember that you're made of atoms forged in stars, held together by forces that propagate at the speed of light, perceiving the world through light that travels at that same speed. Remember that you're embedded in space-time, moving through it at 1 second per second from your own perspective, forever chasing a present you can never quite reach, but always inhabit. And remember that you have the ability to understand all of this, to grasp these cosmic principles, and see yourself as part of the larger picture. That's extraordinary. That's cause for wonder. The speed of light wasn't decided by any person. It was decided by the universe itself, by whatever process brought space-time into existence, by the fundamental structure of reality. But you decided to understand it. You decided to engage with these questions. And in doing so, you've participated in one of humanity's greatest achievements, the quest to comprehend the cosmos. That quest continues, and you're part of it. Never forget that. We're approaching the end of our journey, and I want to tackle the biggest, most fundamental questions head-on. Questions that don't have definitive answers, but are worth asking because they push us to the edges of understanding. Questions about why the universe exists at all, why it has the laws it has, and what role the speed of light plays in the deepest mysteries of existence. Let's start with the most basic question. Why is there something rather than nothing? Why does the universe exist? This is a question that science can't fully answer because science explains how things work, not why they exist in the first place. But we can explore what the existence of the universe implies. The fact that there is a universe with laws, with structure, with constants like the speed of light, tells us that reality is comprehensible. It follows rules. It's not random chaos. And those rules are mathematical. The laws of physics can be written as equations, relationships between quantities that hold universally. Why should reality be mathematical? Why should it follow laws at all? Some physicists and philosophers think mathematics is discovered, that mathematical truths exist independently of human minds, in some abstract realm, and physical laws are reflections of these mathematical truths. Others think mathematics is invented, a language we created to describe patterns we observe, and the match between math and physics is because we tailored our math to fit our observations. This is an ancient debate, but it has implications. If mathematics is discovered, if physical laws are mathematical necessities, then maybe the universe exists because it must, because mathematical existence is the only kind of existence. Maybe the question, why is there something rather than nothing, is misguided because nothing is mathematically impossible or incoherent. This is speculative philosophy, not science, but it's a way of thinking about why the speed of light and other constants have the values they do. Another approach is the multiverse. If there are countless universes with different physical laws and constants, then our universe is just one among many. And we find ourselves in this one because it's the kind that permits observers like us. Universes with speeds of light that are too different wouldn't have stars, chemistry, life, consciousness. So we necessarily observe a universe with the right speed of light, not because it's special, but because we couldn't exist in the other ones. This is the anthropic principle taken to its logical extreme. It doesn't explain why the multiverse exists, or why it generates universes with different constants, but it removes the apparent fine-tuning problem by saying all possibilities are realized somewhere. But maybe there's only one possible universe. Maybe the laws of physics are the only logically consistent set of laws, and the constants have the values they do, because any other values would create contradictions or instabilities. This is the dream of a theory of everything, a single equation or principle from which all of physics emerges necessarily. String theory is an attempt at this, suggesting that the fundamental objects are tiny vibrating strings, and the properties of particles and forces, including the speed of light, emerge from how these strings vibrate and interact. If string theory is correct, and if it uniquely determines the constants, then the speed of light is what it is, because it couldn't be otherwise. But string theory isn't confirmed, and it might allow for many different vacuum states, effectively bringing back the multiverse. Here's another angle. What if the universe is a simulation? What if we're living in a computer simulation created by some advanced civilization? In that case, the speed of light would be a parameter set by the programmers, a limit imposed to keep the simulation computationally tractable. If the simulated universe allowed infinite speeds, causality would be instantaneous everywhere, and the computational cost of simulating it would be enormous. By imposing a speed limit, the simulation can be parallelized. Regions of space that are causally disconnected can be computed separately. This is wild speculation, but it's an interesting way to think about why there might be a cosmic speed limit. Of course, this just pushes the question back. Why does the universe that's running the simulation exist? And why does it have the computational principles it has? The simulation hypothesis doesn't answer the ultimate question. It just defers it.